In this video, we'll use Sigma7 Plus version 7 to perform mechanical analysis and use the notch filter, anti-resonance filter, and vibration suppression filter. Hi, I'm Matt Pelletier. Here's a quick preview of what we'll do in this video. After an overview of the tuning filters, we'll use the mechanical analysis function on the z-axis of the demo to determine what resonant frequencies might exist. Then we'll look at 3 different example mechanisms to set the notch filter, the anti-resonance filter, and vibration suppression filter, using the custom tuning window and editing some of the parameters directly. So get connected to your remote demo and follow along with me, and let's start filtering. This chart shows the frequency spectrum of a machine from low to high. Every machine has some level of mechanical compliance and may tend to vibrate at certain frequencies. Filtering makes sure the servo control loops don't cause the motor to apply torque at those problem frequencies. This way, the machine can still be used throughout the rest of the frequency spectrum and improving performance and response. Now there's a low-pass filter not shown here that just cuts off the maximum frequency response, but then the next highest frequency filter is called the notch filter, and it's good for covering frequencies about 500 Hz and above. Resonant problems in the mid-range frequency are covered by the anti-resonance filter, and at the lower end, all the way down to 1 Hz, into the tens of Hertz, is the vibration suppression filter. And you see there is some overlap between these filters. The frequency parameters for each filters do have a range, but they're often better implemented in the middle of their range. And here we're listing all of the different parameters just for completeness. We'll be looking at these more closely as we look at how to implement each of these filters. So the big question is, how does my mechanism respond across the entire frequency spectrum? And to help you find this, Sigma7 Plus has a tool called Mechanical Analysis. And this software tool will cause the amplifier to generate its own internal torque reference frequency, sweeping from very low frequency to very high frequency. It'll run that through the motor, which is coupled to the machine, and the machine will move a little bit, and this function records the output. And it may find that at some frequencies there tends to be an increase in amplitude, and at other frequencies perhaps a decrease in amplitude out based on the properties of this mechanism. Any frequencies that have a high gain may require filtering, and if you enable the servo and you get this kind of oscillation or noise, you really need to take care of that before you can go on to do any other tuning. Oftentimes the auto-tuning will catch this and automatically apply it, but we do need to know how to apply these and understand each of these filters. But there's much to be learned by doing what we call this FFT, fast Fourier transform measurement, where we plot the gain versus frequency and look for peaks in this graph that indicate there is a problem at that frequency. This type of graph is called a Bode plot, and those 3 filters will then be able to be used based on the frequency that's found in the mechanical analysis. We'll also have a pretty good idea which of those 3 algorithms are the most appropriate to apply to the machine. Let's go try this out now in Sigma7 Plus version 7. I've got connection to the z-axis here, the SGD7S, and we got connection here to the remote demo. And one thing you're going to want to do on this demo is get some audio feedback. You'll want to hear the chirps that go through the motor. That's instructive. You can do that with this speaker icon that says Open Audio. Be sure there's not a line going through it, and then you'll be able to hear with the microphone that's on this webcam. And then what I do is minimize Sigma7 Plus a little bit and set it up so I can peek at that motor while I'm using Sigma7 Plus. Now under the menu, and mechanical analysis is under the solution category, mechanical analysis. The motor will move. Let's open this and then click Start. So what are we looking at here? There's a vertical mode selection just to be sure that the motor doesn't fall if you have a vertical load. You have the sampling time. And the sampling time determines the maximum measurement frequency. So the first time you do this, it's a good idea to leave this back at the default so you get the maximum measurement frequency. And then later you can do another graph if the problem frequencies happen to be in the lower range. Down here, the excitation amplitude is the percent of torque. 50% is pretty good. You can go higher, but you don't want to risk damage to the machine. And if your motor has been oversized or there's a torque limit in place, you may even want to reduce this. The allowable rotations is just to be sure that the motor doesn't go too far and run the mechanism into the hard stop. And you might do more than one measurement to interpolate the results between a number of measurements. For this first time, let's leave all this at default and just go ahead and click Next and Start. This is a function of the servo itself. Keep clicking through it. You click servo on and forward. Did you hear that? Saw the motor move a little bit. We'll do it again in the reverse direction. Moves a little bit. There's a little chirp. That's the sound of all of the frequencies going through the system. And you finish it. So what we have here now is the gain versus frequency for this wheel. There are some automatic measurements. I'm just going to clear those out. I hope you'll agree that this mechanical analysis is quite distinct from the other one I showed in the PowerPoint slide. There really is no peak, if you would. There's no big spike in the gain. It does kind of trend down. The other part of this graph, however, is called the phase. And when the phase goes below 180 degrees, that's another good indicator that that might be a problem frequency. Right here, this is happening. And you're able to open this cursor button and drag around, look at different points. You can click a couple cursors down. You can see this frequency right here is 2000 hertz. There's another tab here for notch filter setting. This tool is estimating a notch filter frequency of 3100 hertz, which is indicated by this pink line. So in other words, it's at the very upper limit of this measurement. Probably this wheel does not need a notch filter. After all, I don't imagine there's much mechanical compliance since it's just one wheel rigidly attached to the shaft of the motor. But since we're learning about filters, why don't we try this out? Let's click Setting. And that sets the notch filter for us, gives us the parameter 409. And a good practice here is to also save this mechanical analysis file. Let's do that. This way you have a snapshot of the mechanical performance for comparison as the machine wears over time. What is this notch filter that we just set? Well, it's a way to filter out a narrow band of frequencies at the input to the torque loop. And it allows both lower frequencies and higher frequencies to pass through, just not that problematic frequency. And as we mentioned, it's best used above 500 hertz. In fact, we even have an automatic notch filter in Sigma7 that if there's vibration, it will detect it and set the notch filter for you automatically. We have up to 5 notch filters. Let's take a look at the notch filter parameters in Sigma7 Plus version 7. You can close out the mechanical analysis. Just go to Edit Parameters. Since the notch filter acts at the torque loop, we can go to the torque category. And here you can see all of the notch filter selections and frequency. There's the frequency that we set. 3109. There's a Q value and a depth. Each of these 5 notch filters has a corresponding selection parameter to turn it on and off. There's most importantly then the frequency. That's the center frequency for that notch filter. This depth is just a multiplier for the strength of the filter, and the Q value is like a depth to width ratio. Depth and Q value can be left at default most of the time. If you go to extremes with these parameters, you can cause vibration in the system or make it too sensitive to the slightest mechanical change. Now let's look at an example of a ball screw actuator. Got the motor and the coupling and a ball screw. It's really an XY table. There's the Y-axis mounted on top, but we'll just focus on this lower X-axis. And in Sigma7 Plus, we've provided you with the mechanical analysis file. Use one of your offline axes here in the menu. You can go to mechanical analysis just to open up this file. Got file open, and then take a look in your class materials for the mechanical analysis folder, and let's open up the ball screw mechanical analysis. We can clear out these cursors and you put down your own. Where do you think might be a problem frequency on this mechanism? Probably right here at this peak. If you click down the cursor and look at the cursor position, what frequency is that? Mine ended up at 1175 Hertz. And you see this also corresponds to the location where the phase inverts from -180 to +180, meaning that the load vibration is driving the motor opposite the direction of the torque command. What filter applies to this frequency range? The notch filter. This really is your classic example of the notch filter. In this particular case, I didn't really have to do anything to apply the notch filter. The actuator made a loud squeak for about 1 second, and the automatic notch filter turned on these settings that you see here. It did set a torque reference filter, slightly different than the default, enabled notch filter 2, set the frequency to 1240, it's pretty close to what we measured, and even did an adjustment on the Q value. And after that, it moved quite nicely and without any more noise. So that's the notch filter. Notch filters have been around for a pretty long time, and between the mechanical analysis method of setting it and the automatic setting, there's probably not a lot you need to do with the notch filters. They almost take care of themselves. If you are really trying to tune an axis for very high performance, later on it may be that the machine is also able to vibrate at a slightly different frequency, and you may have to adjust the center frequency of the notch filter later on in tuning, and you'll be able to get a little more performance than out of the mechanism. Now let's move on to the anti-resonance filter. Do you remember the target frequency range for this anti-resonance filter? 100 to 500 Hertz, although it can go beyond that. You can see in this graphical example the vibration in the torque signal during motion before anti-resonance, and then how that's reduced with anti-resonance on. Okay, to get to anti-resonance in Sigma7 Plus, you need to get to the custom tuning screen. So let's close out what we have here and start fresh on the Z-axis. Go down here to the tuning menu and click execute. All this time we've been using the tuningless method of tuning, the adaptive tuning. So we need to turn that off to get to this screen. Let's click OK. Power supply returning on means we'll have to cycle power. So let's do that. Remember, to cycle power, you can just come into the software reset and click execute. Just takes a few seconds. Okay. And after that, we can come back to the menu and go to tuning a second time and execute. And the screen is a little different now. Let's skip to the bottom here, advanced adjustment. And OK to the warning. Click custom tuning. There's going to be a few screens here to get through. Just click next for now. In a different video, we'll show you guys how to do all of the tuning options here. This moment of inertial ratio is about 26 to 1, so you put in 2600% and next. And this is where we want to be at the custom tuning panel. A little bit of a preview into the custom tuning method, which again we'll go through in another video. So for now, please focus on the bottom section where you see those three filters: notch filter, anti-resonance, and vibration suppression. If there really was vibration, the anti-resonance control adjustment would light up, drawing your attention to this button. Let's just go to this button here anyway. And since we don't have vibration, we can go to manual set, where you're able to set frequency and damping gain. Let's set it up for this rotary drive example. We've got this machine in the tuning lab. It's just a larger motor directly connected through a coupling to a wheel. Let's now look at the mechanical analysis file for this machine. Sigma7 Plus, you can get that through the menu of the other servo axis, mechanical analysis, and open that up. And this is called the rotary drive mechanical analysis. It's open. We can clear out this auto measurement and put on your own cursor here. What is the resonant frequency? See if you can find this by yourself. The resonant frequency is, according to my cursor, 344 Hertz. There's a pretty distinct peak right here in the gain plot, and the phase gets really messy after that frequency as well. So what filter applies for a frequency of 344 Hertz? Anti-resonance. When the frequency is low like this, that's a good example of a time that you could change your setup and run a lower mechanical analysis. So how about we open that other file, go to open file here, and let's go to mechanical analysis for the rotary drive, file number 2. Here you see the measurement conditions. I had set the sampling time to 625 microseconds. And if you want, you could go back and do that on the demo. And we'll clear this out and put in our cursor again. We have a center frequency. Looks like it's more like 343.81. Yeah, still about 344 Hertz. All right, let's implement this on our demo axis here. I know it doesn't need it, but just so you can go and see how this tool works. You can go back to your anti-resonance control adjustment window that we had open, and you would turn it up to 344, and then you click Start Adjustment and start to increase the damping gain until the noise goes away. And you don't want too much damping gain, so you would turn it down until the noise starts to come back, and then turn it up until the noise goes away. You want to find a value that dampens the system, but you don't want that too high just because it could interfere with the performance of the system itself. So you set these parameters, click Finish. This is just a nicer interface. You could set the parameters directly. In fact, let's go see what those parameters are. Click Completed. Complete that. Let's close this all out and edit parameters. Okay, anti-resonance is not a torque parameter. Instead, it is a gain parameter in the PN100s. Down here at the bottom of the list, anti-resonance frequency. There's our value set and the damping gain that we set. And again, this filter to turn it on. Sometimes it's easier just to compare that to the defaults. And in the display comparison, you can see these parameters that we've set for anti-resonance control to turn that on, to set the frequency, and damping gain. For the lowest vibration frequencies, we have vibration suppression. Low frequency vibration in a machine in the ones of hertz, tens of hertz is particularly troublesome because this is within the machine's operating frequency range. This type of vibration can be particularly noticeable at the start and end of a move, where you'll see speed and position error have this somewhat of a sinusoidal vibration. If your machine is set up like this test station we have here, with a long threaded rod and a heavy weight at the end, this is the kind of response you'll get without vibration suppression. With vibration suppression, it's greatly reduced. Now you might think, who designs a machine this way? Of course it's going to vibrate. So let me show you a real life example here. This machine that takes plates of glass and has to insert them into maybe an oven or a storage rack. And the product itself is just prone to vibration. Another factor is just very large machines will tend to have lower vibration frequencies due to their size. So it is a real problem, and it can be advantageous for compact machine design or some other design constraint that the actuator must be located somewhat at a distance from the actual workpiece. So if the machine designer is able to confidently make this type of machine, knowing that vibration will not be an issue, it can remove a lot of those design constraints and result in better performing machines. So how does vibration suppression work? From a conceptual standpoint, I think we can explain it like this. If you were to move a pendulum from point A to point B very slowly, I think you can imagine that it would be not too hard to move with a minimal oscillation at the end of the move. But if you need to move quickly and just stop your hand there, I think you know from experience that the pendulum will swing back and forth for a very long time. So how could you compensate for that? Well, if you think about canceling out that oscillation by perhaps pulling back with your hand, you can kind of cancel out that oscillation by getting the right rhythm, so to speak, with your hand. This same idea, this same concept is what's going on with vibration suppression. However, it has to be mathematically modeled, and that's our vibration suppression function. As you saw in the previous section, vibration suppression is also accessed through the custom tuning function. So let's pull that up now in Sigma7 Plus. We can close this that we had up before. We don't need to save these changes. And let's open up the tuning, execute, advanced adjustment, custom tuning, click next, 2600, click next. And down at the bottom, let's give this demo some vibration suppression also. Vibe suppress. If the machine was in motion and it was oscillating at the end of the move, you would see this residual vibration frequency detected, and you could import it. For the purposes of this training, let's look at this example of a Sigma track linear motor with two threaded rods with a load at the end. It's the same mass, same rod, different lengths. And I think you'll agree that the longer rod will be vibrating at a lower frequency and the shorter rod will be vibrating at a higher frequency. And let's use Sigma7 Plus. Again, the unused axis here for now. We can pull up the mechanical analysis again. And let's open up the Sigma Track mechanical analysis. This was the mechanical analysis at the default settings. And it's not showing a lot. So I went ahead and did another measurement, knowing that vibration would be an issue at low frequencies. I did the lowest possible. Let's open that one. analysis number 2. So this mechanical analysis only scanned up to a little over 100 hertz. So let me ask you, what frequencies look like they have something of a disturbance in the gain or the phase? Activate your cursor. Let's see what those frequencies are. Looks like the gain has a little dip right about here. The phase has a little disturbance there also. And then also up here, there's a little disturbance. And those two cursors read in at a little under 6 hertz and a little under 22 hertz. So you pull up the vibration suppression window. Which of those two frequencies would you put in there? And what will happen is if you have two frequencies like this, you pick one. For example, let's go with the 6 hertz and hit set. And I get this timeout error. And that's because you do need to have the servo on when you set the vibration suppression through this function here. We can do that, click OK here, we can do that through program jog and run that, turn the servo on. It needs to see that the motor does get into position, and without the servo on it may not be in position. So we'll try this again here. Let's go down to what we were going to set it as, 6 hertz, and set. Okay, we can set one frequency through this interface. And you would do this while you're running the load, and you would find the frequency that's given to you here. This number's just coming up. I'm not running the load, so that doesn't apply. You would find the frequency and visually look to see that the vibration is reducing. And when you've dialed in the right frequency, then you finish it off. And a second frequency can be set manually. We were going to set 21.84. We can do that in the Edit Parameters window. We should complete this, not cancel it. Close this function. It was 22 hertz. Okay, there's the warning. Finish this off. And again, the gain parameters include the PN140s. You see here it says, do use model following control. It's important that that one's on. Vibration suppression is part of model following. So now vibration suppression has been turned on. Here's the 6 hertz frequency that we just set. And you see there is a vibration suppression number 2 frequency. And we'll need to set this one, but you also need to turn it on. That's under PN140 digit 1. Perform vibration suppression over 2 specific frequencies. So change it to 2 frequencies. That activates suppression frequency number 2. So that's 220 tenths of a hertz. And looks like there's a correction factor that you could also apply. And we can write all those in. To this poor demo wheel that's now set up for a notch filter, an anti-resonance filter, and a vibration suppression filter, and it doesn't really need any of them. And just to conclude this, let's run this motor and see what it does. Close this off. So we'll start by getting the program jog ready to go. Program jog. We have this move set up from the previous video. I'm going to just change it to 1 time movement. And we'll run a trace. And I will set up for checking the speed reference over 750 microseconds. Start that trace. Now run this program jog 1 time. Okay, we got the graph, and you see that the servo is applying a torque to cancel out the expected vibrations. Maybe I'll just save that for comparison. Now let's take all those filters off. One last time here, advanced adjustment, custom tuning, and make our way here to the custom tuning panel. You see that you can very easily cancel the notch filter, cancel the vibration suppression, and click completed and finish. And now start this trace again. Execute again. But you see a distinct difference, and I think you'll agree that this motor, which does not have resonance or vibration, is better off without those filters. So you don't want to put those filters on if you don't need them. And one thing that's kind of cool here, the data trace, is this overlapping. You can put in these two and compare them. See, there's a definite reason not to put on filters that you don't need. I hope this tutorial has given you a better understanding and a hands-on experience now with using these filters. There's a tuning video for each of these machines we have in the lab, where I talk through the entire process from beginning to end. And of course, these machines are part of our tuning lab for the training class that we run here at YASKAWA. Thank you for watching this video. For more information on Sigma7, please go to yaskawa.com. Products, Sigma7 Servo Products.